In the race for ever larger models, we often forget that standard hardware has strict physical limits. How do we run a state-of-the-art model locally on a smartphone or a laptop without exhausting its memory? Meet Gemma 4E2B, featuring per-layer embeddings, or PLE. The E in E2B stands for effective parameters. By decoupling memory lookup from active floating-point matrix multiplications, per-layer embeddings allow a model with just a 2 billion active compute core to deliver the representation quality and reasoning of a much larger network. In this video, we will dive deep into this architectural shift, from standard input embedding bottlenecks to layer-specific gating, effective parameter math, multimodal scaling, and edge device memory optimizations. Let's get started. Let us first understand the problem per-layer embeddings solve, the traditional embedding bottleneck. In a typical transformer, we have a single, massive input embedding table. When text enters the model, each token index is looked up in this table to retrieve a single high-dimensional vector. This vector must carry all semantic, syntactic, and structural information through the entire network. To handle broad, multilingual vocabularies, modern models like Gemma use vocabulary sizes of over 256,000 tokens. This means the embedding table alone contains billions of weights, consuming hundreds of megabytes of space. Yet, these parameters are only accessed once, at the very beginning of the network. As the signal passes through deeper layers, these massive matrices sit idle in memory, wasting precious edge storage and bandwidth. Let's visualize this traditional pipeline. Per-layer embeddings, or PLE, completely re-engineers this pipeline. Instead of a single massive input embedding table, PLE distributes the embedding parameters across the entire model. Each individual decoder layer is given its own small, specialized token embedding lookup. As the hidden representation passes through the network, it is dynamically combined with layer-specific token vectors. This means the model does not have to carry a single static representation from the start. Instead, token-level details are progressively injected and refined layer by layer. This progressive refinement matches the depth of semantic processing, allowing the model to perform highly complex reasoning with a much smaller active compute core. How does this look under the hood? Inside each decoder block, PLE utilizes a gated residual update. During the forward pass, a parallel, lower-dimensional conditioning pathway runs alongside the main residual stream. First, the token identity is used to look up the layer's specific embedding vector. Simultaneously, the block's current hidden state is projected to generate a gating signal. An element-wise multiplication modulates the token vector with this gating signal, ensuring contextual alignment. Finally, this gated vector is projected back to match the hidden dimension of the main stream, and added as a residual update. This gating mechanism is crucial. It prevents signal distortion by ensuring token information is only injected when it is relevant to the surrounding context. Let's look at the mathematics. This brings us to the core of the parameter naming. In deep learning, parameter count has traditionally been directly tied to inference speed. Scaling a model to 10 billion parameters multiplies the computational cost. However, parameters in attention and feed-forward layers are highly compute-intensive, requiring dense floating-point operations, or flops. Embedding tables, on the other hand, are simple lookups. They require memory bandwidth but virtually zero compute during inference. PLE exploits this asymmetry. By placing billions of parameters into distributed, layer-specific lookup tables, Gemma 4e2b achieves the representation capacity of a much larger model, while keeping its active compute core at only 2 billion parameters. It runs with the speed of a 2 billion parameter model, but has the knowledge capacity of a much larger network. Since PLE parameters are accessed via simple index lookups rather than dense matrix operations, they open up unique optimizations for memory layout and quantization. In standard models, quantizing active weights below 4 bits causes severe degradation in reasoning. But PLE parameters can be quantized heavily, or even stored in lower precision formats like FP4 or blockwise integers, because they do not participate in deep accumulated dot products. Furthermore, because these tables are only indexed at each layer, they can be cached in slower, high-capacity system memory and loaded on demand, saving precious high-speed GPU or NPU SRAM. This makes on-device deployment incredibly efficient, preventing the model from exceeding standard memory limits during edge inference. Gemma 4e2b is a natively multimodal model, capable of processing text, images, and audio. PLE plays a major role in scaling this multimodality. When processing diverse modalities, the vocabulary size grows significantly as we add specialized visual and audio tokens. In standard architectures, this would result in a massive expansion of the input embedding table, worsening the idle parameter problem. In Gemma 4's PLE setup, the per-layer embeddings can be tailored specifically to different modalities. For example, text and image tokens can have distinct gating behaviors or specialized dimensions across layers. This structural modularity allows the model to handle diverse inputs efficiently, preserving representation quality without bloating the inference compute loop. Training a model with per-layer embeddings presents unique optimization challenges. In standard models, gradients for the embedding table only flow from the first layer, making it straightforward to optimize. In a PLE model, because lookups are distributed across all layers, gradients flow back to different embedding tables from every single decoder block. This requires specialized learning rate scheduling and gradient clipping to prevent embedding table divergence. Researchers use initialization schemes where PLE weights are scaled inversely with layer depth, ensuring that deep tables do not saturate the activations. This balanced optimization ensures that early layers focus on structural syntax, while deeper layers learn highly abstract semantic associations, leading to superior overall convergence. How does Gemma 4e2b perform in benchmark comparisons? The results show that the PLE architecture delivers incredible intelligence density. On reasoning benchmarks like GSM-8K and math, the E2B model achieves performance that matches or exceeds traditional models with 4 to 6 billion parameters, despite having only 2 billion active parameters. On code generation benchmarks like HumanEval, E2B scores 78%, beating older models twice its size. In long context retrieval, PLE's progressive refinement allows E2B to easily pass the needle in a haystack test up to 128,000 tokens. This proves that decoupling active compute from parameter scale is the most efficient path forward for on-device reasoning. Per-layer embeddings represent a fundamental shift in how we design language models for resource-constrained edge environments. By distributing token representations throughout the model and utilizing a gated residual update, PLE decouples parameter capacity from active inference compute. The success of Gemma 4e2b proves that we can build highly capable, edge-optimized models that deliver frontier-level reasoning on consumer hardware. As AI continues to move from centralized servers to local, private edge devices, architectures like PLE will be key to making offline, highly smart models accessible to everyone. Thank you for watching. If you found this architectural breakdown valuable, subscribe for more technical deep dives into the models shaping the future of AI engineering.